Hello and welcome. In this video, we will discuss vibrational motion, one-dimensional harmonic oscillator. This is the part 1 video. So we have to discuss vibrational motion and that of a one-dimensional harmonic oscillator. So the aim of this video is to discuss the setting up of Schrodinger wave equation of such a system. So before setting up the Schrodinger wave equation, we have to discuss what is a simple harmonic oscillator. Simple harmonic oscillator you might have studied in your plus 2 classes as well as a BSc subsidiary classes, that if we have a support like this and to which a mass m is attached by a string, this is mass m, this system can undergo oscillation in this way. That is, this is the extreme left and this is the extreme right of the oscillation. So such a system is an approximation to a simple harmonic oscillator, or such a system will execute what is called a simple harmonic motion. A simple harmonic motion is a motion in which the acceleration at any point is directly proportional to the displacement from the mean position and is always directed to the mean position. That is the exact definition of a simple harmonic motion or oscillation. That is, acceleration is a second derivative of displacement with respect to time. The acceleration is directly proportional to the displacement from the mean position. Say x is a displacement. And we know that force is equal to mass into acceleration. And if we plug this equation into this equation, we get F is equal to mass into d square x by dt squared. So in a simple harmonic motion, the acceleration at any point is directly proportional to the displacement from the mean position and is always directed towards the mean position. So there is always a force which is directed towards the mean position. And this force is directly proportional to the displacement from the mean position. And that force is termed as a restoring force. That is, a restoring force F of R, say restoring, is directly proportional to x. That is where x is the displacement from the mean position. But we know that from Newton's law, F is ma, mass into acceleration, is directly proportional to the displacement from the mean position x. And for acceleration, we will plug this equation into this one. So we get m into d square x by dt squared, m into the second derivative of x with respect to time is directly proportional to the mean displacement from the mean position x. Now we can replace this proportionality sign by a constant of proportionality, and this implies that m into d squared x by dt squared is equal to minus k into x. This minus sign shows that this force, that is the restoring force, is always opposed to the displacement, and this k is termed as the force constant. Is termed as the force constant. Thus we have m into d squared x by dt squared is equal to minus kx. Upon rearranging d square x by dt squared plus k by m into x is equal to 0. Now we can substitute for this k by m, say d squared x by dt squared plus a squared into x is equal to 0, where a squared is equal to k by m, which implies a is equal to root of k by m. Now, this is in the form of a standard second order differential equation. We know that the standard second order differential form is always in the form of d square psi by dx squared plus k squared psi is equal to 0, where psi is a function of x only. So this is a standard second order differential equation whose solution is given by psi of x is given by, say, some coefficient a cos kx plus b sin kx. Either of these two functions or a linear combination of these two functions will be the solution of the standard second order differential equation. In the same way, we can write the solution of this differential equation as x is equal to, say, a coefficient a into cos at plus sin at. Here a is given by root of k by m. So in the full form, the equation will be x is equal to a cos root of k by m into t plus b sin under root k by m into t. Now you see here, this term root of k by m into t. Here also root of k by m into t. These two factors, they are reciprocal. They should be reciprocal to each other. So that means that this root of k by m should be time inverse, or this should be a frequency term. In the same manner also here, root of k by m should be time inverse. It should be related to the frequency term. Time inverse means it is a frequency. So this equation can be compared to, say, a periodic sine wave or any other periodic motion which repeats in every 2 pi radian. So in that case, we will write x as, here x is a displacement or it is the amplitude function. Here x is always the amplitude function. X is the amplitude function. Why it is amplitude function means it shows the displacement from a mean position. Suppose this is the mean position, mean line or the mean position, then the particle is capable of oscillating towards the either side of the mean position, and therefore this displacement may be referred to as an amplitude function. And the thing should be noted here is that any displacement from any mean position will be an amplitude function. So such a periodic motion, this simple harmonic motion or a periodic motion, it can be compared with a periodic wave function here. This is a periodic wave function which repeats after every 2 pi radian cycle. And the displacement in that case may be given by either the sine wave equation or the cosine wave equation or the combination of two, whatever it is. It always takes the form, say, a cos 2 pi nu t plus b sin 2 pi nu t. This means that here also we can see that it is a frequency factor, 2 pi into t. Here it is a time. Here also 2 pi into nu. Here it is a time. So these two can be compared with this equation. Here also. Therefore, we can write that 2 pi nu is actually root of k by m. Thus we got 2 pi nu is equal to root of k by m, or we can square this equation and thus rearrange to be 4 pi squared nu squared m, where k is the force constant. Therefore, the force constant is given by this equation. Force constant is given by the equation. Also, the frequency of oscillation is given by 1 by 2 pi root of k by m. This is the frequency nu, and this is the, so we got k is equal to 4 pi squared nu squared m, where k is the force constant and nu is equal to 1 by 2 pi root of k by m, and it is the frequency term. Now we can compare the simple harmonic oscillation as a spring which is attached to a mass m, and if you pull this mass and release, it will start oscillating in an up and down manner, and this will be the equilibrium position, and it will be oscillating about this equilibrium position, and therefore it can be considered as a simple harmonic motion or a simple harmonic oscillation. Now if you pull this mass downward through a displacement x, there will be associated with the system some amount of potential energy. That is, here potential energy is V is never equal to 0, unlike our particle in a one-dimensional box or a particle in a three-dimensional box or a particle on a ring. In all those cases, we have assumed that the potential energy was equal to 0. But in the case of simple harmonic oscillator, such an assumption is not possible because the system is always associated with some amount of potential energy. Now we will see what is that potential energy, by what equation that potential energy is given. That is, V is actually given by half kx squared. V, the potential energy, is given by half kx squared, and it is obtained by a simple integration technique. So our aim was to derive the Schrodinger wave equation for this vibrational motion in a one-dimensional harmonic oscillator. We know that H psi, that is an eigenvalue equation. H psi is given by E into psi, where H is the Hamiltonian, which consists of two parts, say the kinetic energy operator plus the potential energy operator, that is Hamiltonian. Hamiltonian, when operated by the wave function, we will get the energy but multiplied with the same wave function. Now the Hamiltonian is given by H cap is equal to minus H cut square divided by 2m into the second derivative of displacement plus the potential energy. So here we have already stated that potential energy is never equal to 0. Therefore, potential has to be always considered in the Hamiltonian. This H cap is equal to minus H cut square divided by 2m into d square by dx square plus v. Therefore, the eigenvalue equation takes the form minus H cut square divided by 2m into d square by dx squared plus v of psi is equal to E psi. Now we have minus h cut square divided by 2m into d square by dx square plus v of psi is equal to E psi. Now we will operate this psi into the bracket and we will get d square psi by dx square plus here we have expanded the h cut square. So we got 8 pi squared m by h squared into E minus v into psi is equal to 0. Now we know that the potential energy V is equal to half kx squared and k is equal to 4 pi squared nu squared into m. Substituting for k here we get V is equal to half of 4 pi squared nu squared m into x squared. Therefore, the potential energy comes out to be V is equal to 2 pi squared nu squared m into x squared. Now we have to substitute for this potential energy in this equation. Now we have to substitute for potential energy here. Therefore, we get d square psi by dx squared plus 8 pi squared m by h square of E minus, instead of V, we have written 2 pi squared nu squared h squared into m of psi is equal to 0. Now we have to multiply both these terms with this 8 pi squared by m into h squared. That is actually we are opening the bracket here. So we will get d square psi by dx squared plus 8 pi squared m e by h square minus 16 pi raised to 4 nu squared m squared x squared by h squared of psi is equal to 0. Now we will put alpha for this 8 pi squared m e by h square and beta for 4 pi squared nu m by h square by h. Therefore, beta square comes out to be 16 pi raised to 4 nu square m square by h square. So instead of these two terms in the bracket, we have defined alpha and beta and we are substituting inside the bracket. Therefore, we will get d square psi by dx square plus alpha minus beta squared x squared of psi is equal to 0. Now, we have to solve this equation. So, this equation cannot be directly solved. Therefore, in order to solve this equation, we will transform this equation into a new variable, that is y. Here the variable is x. Here the wave function changes with x. Therefore, here the variable is x. So, in order to solve this equation, we will change the variable of this equation. How that is done? This is done by defining a new variable. Say y is equal to root of beta into x. Root of beta into x. Therefore, what is dy? Dy will be root of beta into dx. Here beta is a constant. Root of beta is a constant. And on rearranging this equation, we get reciprocal of dx is equal to root of beta into reciprocal of dy. Or we can write it as d by dx is equal to root of beta into d by dy. Upon squaring this equation, we get d square by dx squared is equal to beta into d square by dy square. And we call it as equation number 2. We have already have this equation, that is d square psi by dx squared plus alpha minus beta square x squared of psi is equal to 0. We have labeled this as equation number 1. And now we have to change the variable of equation 1 from x to y. For that, we will substitute or we will plug in equation 2 into equation 1 and we will get beta into d square psi by dy squared plus alpha minus beta squared into y squared by beta of psi is equal to 0. Here instead of x squared, we have written y squared by beta, and that is obtained by this equation. Y is equal to root of beta x. Therefore, y squared by beta is equal to x squared. Actually, we have squared this equation and just rearranged, and we have found the value for x squared in terms of y and beta, and we have substituted here. And now the new equation is beta into d square by dy squared plus alpha minus y squared beta of y is equal to 0. We will put that equation as number 3. Now, dividing throughout by beta, we get d square by dy squared plus alpha is divided by beta, so alpha by beta minus y squared beta by beta is y squared of psi is equal to 0. This is equation number 4, and remember that y is equal to root of beta by x. Now, equation 4 is an equation in variable y, new variable y. So we have switched over from variable x to y, and we have defined y as root of beta into x. And this equation 4 is the Schrodinger wave equation, which is to be solved.